many of you know who this guy, Pavlov is? Okay, so basically we are getting to reinforcement learning, which is actually well studied under the name classical conditioning by Ivan Pavlov. And so, in fact, we talk about Pavlovian reflexes. Okay, you show some state, you do, for example. So that's what is happening, except like sitting here is who's playing Go. But an interesting point to keep in mind as we look at this is that, and this is sort of reconstructing cartoons, that we are talking here about reflex actions. Okay, so the dog supposedly, I mean to the extent you remove this other interpretation, the dog is supposedly being conditioned to drool when it is shown some taste of treat, even before it actually experiences the reward, essentially. Right? So, in some sense, what is happening there is the dog is becoming a quote-unquote reflex agent. Okay. One of the things that you see as we go in the class today is that early work on reinforcement learning from psychology, classical conditioning, reinforcement learning from psychology, focus mostly on reflex responses. So it's as if there is a psychological theory for generating reflex agents, at least training reflex agents. But the interesting thing is we believe that we are much more than reflex agents. In particular, we saw the intelligent agent architecture where there is a reflex agent which is like the earliest part, and then by the end we are talking about this deliberative agent which sort of looks at what the goal is, what the state is, and what it needs to do. Okay, so a deliberative dog would essentially plan to get out of this, slap the guy, and then actually go get some candy and whatever from the shop itself, as against just reflexively only reacting to its stimuli. Okay. By the way, remember you also must have heard a lot of times about this stimulus response, right? What is stimulus response? Stimulus is a particular state being presented to you. Response is your reflex action. So stimulus response is sort of reflex agents. Okay. However, we are actually doing this after having done MDPs. So in fact, one of the things that should come up, hopefully, is that actually there is a version of reinforcement learning that involves deliberation. Okay. Historically, actually, there was, in fact, we'll see in a minute, but there are these two different kinds of reinforcement learning that we will make the distinction of today, and in fact, that's like a big deal in the reinforcement learning. Model-based versus model-free. Okay. To give away a bit of the, like the climax and suspense, model-based essentially means the agent has the transition model from the MDP point of view. It has the transition model and the reward model in its head, just like MDP agent had. Okay. Model-free means the agent has no idea of the transition model. Neither does it have no idea of the reward model. I mean, that means it doesn't have it in its head. It can experience it, but it doesn't have it in its head. Okay. Instead, what it does is it just looking at a particular state, it will just do the right action there. So, if you think from the point of view of MDP, which you should be thinking about, model-free directly learns the policy. Just directly learns the policy. If I'm in this state, I should do this action. If I'm in this state, I should do this other action. Whereas a model-based agent learns the transition and the reward functions and goes back to your value and policy iteration algorithms to compute the policy. Do you see what I'm saying? Okay, I'll repeat this again, but this is the fundamental distinction that you want to get into your head. Model-based versus model-free. Model-based means you know the transition and reward functions in your head. So what that means is you can simulate the world in your head. one of the nicest thing about simulating the world in your head is you don't get physically harmed. You see what I'm saying? So you might say, oh, then I'll do this action. Oh, then I'll fall down. Oh, let's not do this action. Instead, I'll do this action. Whereas if I actually do it in the real world, I will fall down and I'll die. There's a huge difference between thinking versus doing. And the being able to think in your head about where you might be going in terms of various actions, that's what gives us the humongous leverage in terms of intelligent agency. Okay, so that actually is the model-based reinforcement learning. The reason I bring this whole thing up is classical conditioning is essentially model-free reinforcement. So in psychology, they did model-free reinforcement learning without knowing it from the beginning, because that's the thing that they were understanding. In the kind of the AI computer science community, we actually first did the model-based reinforcement and then did the model-free. Right now, both are available. And in fact, understanding the distinction is a very, 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 very important thing that you should do for yourself. Okay, so that's what today's class is really going to be. If nothing else, you should be able to figure out model-based versus model-free in terms of MVPs at the end of today's class. Okay, okay. Now, and then the other thing to pay attention is reinforcement learning is basically what AlphaGo used. Okay, AlphaGo is a reinforcement learning system. It played against itself or played against the cached games, Go games, millions of cached Go games, and then it essentially learned, in fact what it did is a model-free reinforcement learning. It learned a policy. Okay, actually, in fact, I would say, it does have variations of both model-free, mostly actually model-free, but there are some pieces of model-based in it too. And the big difference winds up being that until now, we have been looking at value and policy in tabular representations. You want to keep thinking about this, tabular representations. That means value basically takes a state and gives a value. It's as if there's like a huge big table which has the values of each of the states. And there's a huge big table which has the action to be done in each of the states. Okay, one thing that we will do after these atomic representations where we think of states as block boxes is try to come up with analytical representations are basically functional representations for the value and policy functions. So the idea there would be that if the state has property 1, property 2, property 3, then somehow I make some computation in terms of these properties, out comes the value. So I learned the value function not in this tabular form, but in this sort of functional form, just a second. And what AlphaGo did is it represented those functions as deep neural nets. And neural net is a universal function approximator. We'll talk about it when we get there. Okay, so they learned the value functions they learned, basically they learned as neural networks. And then they used it again as this program instead of, and of course, AG. And they reasoned up it. Okay, so that's another reason why you want to keep track of what's going on in reinforcement learning. Yes?
So, my question is that on the, you said it was slightly model-based or model-free for AlphaGo. Does that mean it just got bored and it just basically didn't know the rules and just like put these?
No, basically, that's a very interesting question. So AlphaGo actually was given rules.
Okay.
I mean, there is a bit of so very few people actually read the AlphaGo paper. They only read the write-ups on AlphaGo in popular press. And the write-ups on AlphaGo in popular press basically make it look as if it's just deep learning. Okay, it's as if it's just function approximation. First of all, it's doing reinforcement. Okay, and secondly, it wasn't completely tabula rasa. It's not starting with a blank slate. Okay, it does actually have rules of the game represented as parts of the features of the state. Okay, but having said that, that's okay. In some sense, actually, the Deep Blue did have feature-based representation for evaluation functions.
So it's basically just like a chess master playing both sides of the board, just to say, oh, this happens, I do this. And
Yeah, no, it has, it has certain parts of the rules of the game were put in. And again, it's much easier to understand AlphaGo from the point of view of min-max search, essentially. It turns out it does a particular kind of min-max search where it does what is called Monte Carlo tree search. Okay? So in fact, it actually combines a whole bunch of ideas that occur in this course, as against just one idea, one trick pony, which is basically neural networks, which are very important idea, but they are not by itself enough. Okay, so so reinforcement learning, we still have an MVP, and we basically have a set of states and a set of actions and a model and a reward function, as if nothing has changed between last class and this class. The only thing that changed is we don't know the T or R. We do not know the transition function or the reward function. So there is an MVP that you are in, but you don't know its parameters. If you know T or R, then it's just an inference problem. There's no learning, it's an inference problem, which is figuring out what is the optimal policy, which you can do by either computing value first and converting it into policy, which is what value iteration is, or directly go with policy, which is what policy iteration is, or compute just the next action that you need to do, which, I don't know if you remember, is how we got into MDP with the real-time dynamic programming. Where remember we went from min-max to MDP with this online search algorithm for MDPs. Okay, and so that is also possible. We don't compute either the full value function or the full value function. We just compute what's the next action to do and let the nature take its course. Then you'll again figure out what my next action is. That's just an online version of computing value also. Okay, those are all things that you can do if you know T or R, but you don't. Okay, so then the question becomes, how am I supposed to work in this world if I don't know the transition and reward function? You learn. Okay, talking about learning, in general, there are two kinds of learning that we will look at. The most, when you take a machine learning course, you typically start with what is called inductive learning, which we will get to probably next class. Okay, where essentially you're generalizing you're trying to capture a function given numbers from that function, some values of that function. So I give you the xy values of the f of xy, so xy values of a function. Then you want to come up with the form of the function. That's the inductive learning. What is happening in reinforcement learning is actually the first and foremost what's happening is you're trying to predict future states, what happens in the future states by changing the expected value of the current state. That's ultimately what winds up happening, as you will see. So in some sense, it's actually sort of an interesting technical point that inductive learning doesn't happen in atomic representations. Because there's nothing, if you have a state which is a number, state 1755 has the following property. How am I supposed to generalize this? Suppose somebody tells me that the student with the following social security number got a C. And this other student with this other social security number got a B. Okay, can I learn some pattern from that? Unless I'm some kind of numerology and add up the digits of the social security number, there's really no pattern to learn. If on the other hand, I define each of these students as the student with the social security number as S1 happened to be essentially already had the prior GPA of this much, did this well in the homework problems, did this well in the project, and this many times he slept or he or she slept in the class. These are all features of the student, and then they got this particular grade. There is a hope. I can actually generalize from that by giving given a new student with their properties, I can guess what their I can predict what their grade is. Do you see what I'm saying? So generally learning requires a representation of the state that is feature based. That state should have structure, otherwise you can't do anything. Even if I give you an entire list of social security numbers of previous students and their grades, if you give me a new student with a new social security number, I have no clue what their grade is going to be. So I don't really think of you as your social security numbers. It might come as a huge surprise to you. I think of you in terms of what you're sleeping in the class, what is your grade, what is your homework, what's your project, whatever. That's how I kind of have an expectation as what your grade is going to be. Yes?
And so these features that you're talking about, like sleeping in the class, doing well on the homework, these are all things that we kind of like expect to correlate to good grades.
That's a very good point. So this is basically state representations, and one of, again, we're kind of jumping ahead a little bit. One of what actually happens in the neural networks, for example, is I could give, remember I said I had the AI-based grading scheme, right? So the AI-based grading scheme would have taken you a photograph. The photograph does have a lot of features of you. It basically has like a whole bunch of pixels, making up your photograph. Way better than a single social security number. And then I have like 1 million students and their grades. And I train a neural network. It finds some patterns. It says when the nose is slightly crooked, it looks like they're getting a C+. Or when their hair is very frilly, they're getting like an A++. That sort of a thing. So don't go and change your hair, but this might be something that it finds. Now, just because it found a pattern doesn't mean that's the pattern I'm using. It just basically tried to fit the data to some features that it could extract from the picture. Now what it is missing, of course, is there is no causal theory. There is no actual causation between nose being slightly crooked and your grade. Now you might actually ask a second order question. Where the heck do causal theories come from? When you came into this world, where did the causal theories come from? Did you know what was causing what? Not necessarily. It turns out, in fact, causal theories are the greatest invention of our civilization, human civilization. That's how we get along. Essentially, somebody figures out a causal theory, other people can use it. We stop caring about black cats coming in front of us, causing large numbers of accidents, because somebody has proved that typically being drunk, etc., have more actual causative connections to you having an accident than a black cat showing up in front of you. Okay, so anyway, so coming back again, we are saying we don't have T and R, and I'm just going to learn the T and R by acting in the environment. Acting in the environment is what you did when you were a kid. That's what you were doing when you were putting every damn thing in your face, in your mouth. Okay, right? Basically, that was like the one sensing capability you have developed. You realize that everything might have a taste, and so put everything in your thing. And then, if anything is looking very red, you'll put your hand on it. And then, if that happens to be a range stove and like a cooking range, then you will learn. Either you learn or you won't be around by now. Basically. Okay, so you are acting in the environment and learning, and this is where actually this whole business about, because kids are acting in the environment, in their living rooms and their kitchens and learning. This is why stabilizing the environment is very important. If you want the kid actually to survive, you remove the guns, you remove the huge big ditches in the living room, you remove any hanging 60-ton weights on the ceiling, just so that they won't necessarily get crushed. I mean, instead of saying, if you're any good at learning, you should have figured this out, we give them a little bit of a break. Okay, if you give them too much of a break, that's what is called coddling. Like if you put humongous big mattresses everywhere, so that the junior cannot even reach anything, right? Then they won't learn anything either. They won't die, but they won't learn anything either. So you are allowing the agent to, you want the agent to act in the environment, and anytime I say act in the environment, you should shake in your boots. Because acting can actually cause real damage. Thinking doesn't. I know some of you think that thinking, heats up the head, and that could be bad. But mostly it doesn't cause any major damage. Acting, on the other hand, can cause damage. Okay, but that's what we do. We actually act in the environment and we figure out what works and what doesn't work. And again, one of these very interesting things is if this is how essentially you're slowly going to learn the transition and the reward functions. One idea is to slowly going to learn the transition and reward functions, and that would be basically called model-based reinforcement learning, because once you get the P and R, then it's just a normal MDP problem. And then you just do the policy or value iteration, or the online MDP. Another idea would be to realize that, okay, I understand that I don't know P and R, but is my goal to find out P and R, or is it something else? What's my goal in life? To act optimally. What I'm looking for is the policy. So why do I care about P and R not being available? So I just go directly learn the policy. It's sort of weirdly similar to the crazy argument that I made at the end of last class, where I said, if all you want is the policy, why are you iterating in the value space? Especially given that the value space is infinitely large. But this is a much more interesting version where you're saying, if all you really cared about is the policy, why don't you just learn it directly? Why don't you learn what action you're supposed to do in each state? And so you short circuit P and R. If you do that, it becomes model-free reinforcement learning. You understand the difference? Again, I'll keep repeating it until you get sick and tired of it, but that's like the most important distinction. And model-free means reflex aging. Model-based means deliberative aging. And you do some things of your life reflexively, some things of your life deliberatively. So you really are a model-free, model-based agent. Okay? Good. Yeah, animals, of course. And then, originally, by the way, it was used in reinforcement learning, was used for backgammon, some years back, and then actually, Jerry Tesoro did this, and that was like a first big, success story of reinforcement learning in computer science. Yeah. Okay. So the objective of the reinforcement learning is that, again, to state, you have effectors and perceptors, you can do actions in the world, you can sense the environment, and you basically, of course, have the world in front of you. Okay? And then sometimes you might have a simulator. This is something, so I try to distinguish between directly acting in the world versus thinking in your head. Right? What do airline pilots do when they try to learn to fly? Right? Do you see what I'm saying? The simulators, the more realistic the simulator is, hopefully the right policy they're going to learn when they actually fly up there. If you make a cheaper simulator, they think, yeah, it looks like good, I'm supposed to just use these arrows, up and down arrows, and it seems to fly. And then you actually get it. My son, who was playing Grand Theft Auto, when he started driving, was slightly surprised that, driving seems to have not too much of a connection with Grand Theft Auto, at least the earlier versions of it. It seemed to have, somewhat, it's lacking in fidelity to the real world. Okay? So if you use Grand Theft Auto as a simulator, you would basically kind of be gone after the first 2 or 3 drives. If you just directly use that policy. But simulators are important. Okay. Okay. So sometimes you might have a simulator, and that will sort of, there is the model based, and then there is a model free, and then simulator is somewhere in between. You can learn the simulator. Okay. Actually, so anyway, then basically, so then you want to just learn how to perform that. Right? That's all you want to do. That means what action should I do in each state? And that is defined in terms of you should do the actions in the state such that the cumulative expected reward is maximized. It's the same MDP. Now, you might actually feel as if I'm being partial to MDPs. I know we did all this A-star search and you threw it out of the window and you're only doing MDPs. Well, MDPs are just generalization of A-star search. So if you understand reinforcement learning with respect to A-star MDPs, you understand it with respect to A-star search. Okay, yes.
Yeah, just one question going back to the simulator. In the video that you guys watched, you talked about the simulators versus the models and using comparative procedural programming versus declarative. I was a little bit confused about the difference then between the simulator.
So that actually brings us to the question of what are some tasks that you guys do, you in the class, just yourself, based on the distinction I made between model-based versus model-free versus simulator-based, which is in between. What are some tasks that you do model-based? And what are some tasks that you do model-free? And what are some tasks that you do simulator-based? We already talked about the simulator-based. Flying seems to be, first you learn it on the simulator, and then you try it out in the airport. So what is the task that you do model-based versus model-free? Yes?
So walking, for example, model-free,
Talking, parts of talking is model-based. The actual, so that's a very interesting point he's making, that when we walk, and my favorite example is swimming, when we swim or walk or any of these things, we don't actually know what the heck we're doing in our head. We don't have a model. Okay, imagine if I asked you, look, so when you fall into the water like this, and then you do this, and then you do this, and then you do this, what will happen to you? Can you tell me? You're all supposed to know, what swimming is. How come you can't figure it out? Another different idea is, like, if you're trying to touch type, and you're trying to type, okay, then you say you have to do accordion. Okay, where will which finger go? The easiest way to do it is to do it. I don't actually know where the crazy keys are. My fingers seem to know. The same with piano. Those of you who learn piano, right, is basically, it seems as if all the good stuff is model free. Right? Piano also is like, if you are extremely good at something, it looks as if it is a skill, S-K-I-L-L, skill, it seems to be model free.
It's not original.
Probably not originally, but eventually learned it as a model free. So that's actually a good point too. Something you may have learned as model based and you compiled it into model free. Some other things were always model free to begin with. Swimming is actually quite hard to do it in model based way because it turns out that the transition function, the reward function is fine. People can tell whether they're sinking or swimming. I'm sorry. But the transition function, the number of actions and their outcomes is just too large. It's just too large. So it looks as if learning this transition and reward function, which is only the intermediate part, is just too costly. So instead you learn how to swim. Just do it, Nike style. Okay? Whereas, if on the other hand, you are running for the presidency of the country, for example, presumably you would do some deliberation. Instead of just saying, just do it, I'll go to the White House and then, I'll feel like doing something on that day. That, at least until very recently, that was not possible. Okay? Right? So it was like presidency was a highly deliberative activity, swimming is a model-free activity, we are getting to a point where obviously things are coming closer, but that's the distinction. Okay, now here's an interesting thing. I actually say the following thing, that a couple of years back, there were just too many online courses. Everybody was taking Coursera courses. Everybody was taking Udacity. And me and my colleagues were really worried. What happens to our jobs? Everybody is taking, Coursera and Udacity. Right? They don't need like a separate room with a bunch of people looking at their laptops have to be taught. Right? So what happens to our jobs? So I came up with this great idea that I'm going to become a swimming instructor. I mean, notwithstanding the fact that I sink like a stone if I try to swim, I see that's where all the money is. Because learning swimming from videos, my friends, is not going to work. Learning swimming from textbooks is also not going to work. Do you see what I'm saying? You need to learn swimming from a swimming instructor who will hit you on their head once in a while and write you correctly. and then you try to slowly sink or swim. And you see what I'm saying? So if you want to be a teacher in the era of Coursera and Udacity, it's better to be a model-free, be a instructor for a model-free task than a model-based task. If it's a model-based task, there should be a Cliff's Notes for it. And anybody can read the Cliff's Notes and then it can be done. Now, here is my question. Why isn't there a Cliff's Notes for swimming? Cliff's Notes for swimming doesn't have to be just text. It could be like a flight simulator. Why isn't there a swimming simulator? How come we have simulators for flying but not for swimming?
Can't really simulate that environment being underwater, rather underwater.
So actually, NASA did simulate spacewalking by pushing people into the water, right? That's how NASA, astronauts would walk inside, huge deep, pools, and because that would give them a sense of loss of gravity. Okay. So actually, the mind-blowing thing is that one day we will have swimming simulators. You just go into this quote-unquote room where there is some viscosity, kind of an air, this kind of viscosity. Presumably, the actual pool is a great swimming simulator, but it also makes you wet and plumb, which are not two good things. Okay, so what you really want to do is to do something that is happening in the air flight simulator, but allow it for swimming. And surprisingly enough, as complex as the flight, I don't know if any of you, when you're going into the flight, you look towards the pilot's cockpit. There seem to be way too many knobs. Way too many knobs. And if you look at it too long, they will probably, the police will come. But it looks like it's a very complex activity. And yet we had a simulator for the flight. Interestingly, the swimming activity is even more complex. The number of knobs you have is continuous motions of your hands and flailing in the water and bobbing up, bobbing down, drinking water, all these stuffs, each of them continuous. 3 milliliters of water drunk, 3 liters of water drunk, 3 gallons of water drunk, big flailing, small flailing. Actually automating that. It's not going to be just a bunch of little knobs and little, it also should be natural. The best way to do it eventually would be that it will be some sort of a augmented reality systems where there will be sensors on your hand and a Kinect or something will be looking at it and will say, you try to swim like this, you'll sink like a stone. And that's what you can do. We don't yet have that. Yes?
If I learned to swim in a swimming simulator, would that become a model-based action?
That's a very interesting thing. So the simulator sort of falls between model-free and model-based. Okay, the point is, there is thinking in your head, there is doing in the world. Simulator kind of gives an approximation to doing in the world without all the problems of actually doing it in the world.